All right. Apologies for the slight delay. I'll get started with a short introduction of myself. I'm Nimish Avarsekar. I am the product manager currently. I'm the product manager for the Query Performance Accelerator team at Greenplum, VmWare, and welcome all of you for a short presentation on how Greenplum, which is inherently based off of PostgreSQL, does partition elimination differently from how PostgreSQL handles it currently. All right, we can get started with a short introduction of how partition elimination works. But before that, I can give a very high overview of what partitions are actually in Postgres. So when you have a table spanning millions of records, it's always wiser to divide them into smaller chunks based on certain conditions in the tuples, and that's what we call them as partitions. So when you create a partition, the table basically creates a child of itself with certain date values, for example, that are supposed to be only specific to that partition. So for example, if you are an organization who wants to create a table for all the orders that you have received in the past 2 years, for example, you might want to consider creating partitions for all the months in that year, so that you can query your data in a much more efficient manner rather than having to do full table scans in your query, right? So partitions enable us to do that. If you want to create partitions based on your month, you can just specify that as a range value, which would mean that all data specific to January will fall only in a specific partition, right? So there are two types of partitions primarily. Range partitions, which are designed based on the range of the date. So you can start with a particular date, end it with a particular date. So all column values within that date will fall in that specific partition. You can also separate it out with a list. So if you want, for example, all the data for March to fall in a specific table, you can specify it as a list of the partitions based on your month column. So there are various ways to design partitions. It depends on your business logic. It depends on how you want to segregate your data. And when you create queries that run on top of these partitions, it's always good to be aware how these partitions are scaled in your warehousing system. So when people ask us about Greenplum is basically a data warehousing system that's built on top of PostgreSQL. So since it's a data warehouse, it's holding a lot of data within it. It can range from a few terabytes to petabytes, and it's so the way Postgres handles data querying, it sometimes may not be applicable to Greenplum. So what we did was we designed a completely new planner for Greenplum that was able to handle that kind of scaling in data when talking about a distributed architecture like Greenplum. Greenplum is basically a shared nothing architecture. It has its own Postgres instances running across the cluster, and they all work together, send data and gather it across in one single Postgres instance on the coordinator, which then displays it out to the query. Okay, so when you look at partitions in PostgreSQL, the way it currently handles it is it's pretty straightforward. If you have a table with say 10 partitions, all it does is it does an append, which is underlying a union or a union all, and it just serializably scans all the partitions based on your partition predicate. Right, so if you have a query on the table without any predicates, it will end up scanning all the partitions and it will display it out. So when you explain the SQL, you will see all the partitions listed out in a format that is That is good in a way, because if you are a DBA or a developer and you want to see which partitions were selected in your query, this is like a good way to kind of check it out. And that's how Postgres has been doing it for a while, right? So in Greenplum, like when you have a use case where you have 50 partitions, 100 partitions, there have been use cases where I've seen 1,000 plus partitions in a table. This kind of a format is not quite scalable. Like you can't really read that explain plan in a way that will make sense. And in some of the conditions, we also started seeing like out of memory conditions, because the plan was just not readable, like because of the sheer size of the partition information that it was dumping. So the Greenplum optimizer, which is its own way of planning things out in a warehousing structure, it introduced two operators which wanted to do this kind of partition explanations in a better way, as it reads out the partition selector and the dynamic table scan. So whenever Greenplum encounters a partition table, like these two operators get initiated, and they get initiated in a sequence. So we also have a sequence operator, which it does basically that, right? So when you have a partition, the sequence operator basically tells the optimizer that you first now need to initiate a partition selector, which basically looks at the partition, it looks at the table, it queries your PG catalog, it gets all the metadata information for the partitions, and if there's a predicate, it kind of does all that scanning. So it says that out of 50 partitions, you're going to need 5 of them. So the partition selector kind of works through that to gather all of that information. So like just for example purpose, we'll take 2 tables, sales, which is a partition table by year, and order data table, which is a completely non-partition table. So we take an extremely simple query, like a select star from sales, which is basically querying your partition table. So when the optimizer sees this form of a query, it initiates a sequence. A sequence is basically just a child executor. So it takes a look at all the childs that are below it, and it executes them in a sequential format. So the optimizer knows that when the partition comes up, like it initiates the partition scan on the scales table, and it also initiates a dynamic table scan on the sales table. Now, since it's a sequence, there is a specific order that has to be followed. So the first form of the order is your partition selector. The partition selector basically looks at the sales table, sees if there is a predicate on the year column, which is your partition selector. If there is no predicate, as in this case, it just does a full scan of your sales table. All right? So it takes all the metadata information from PG catalog and loads it into shared memory. All right? So when it takes all that catalog information, it creates like a hash table in shared memory, which is a key value format, and it loads all the partitions in that table. And it says that, okay, in this case, we need to look at all the 10 partitions in sales, and this has to be now forwarded to the next step, which is your dynamic table scan. All right, so once the shared buffer is loaded with all of this metadata information, we then tell the sequence to go to the next step, which is your DTS. And in the DTS, all this hash table that was created by the partition selector starts to get read into your dynamic table scan. The dynamic table scan is nothing but a sequential scan of the partitions that were like filtered in your hash table in your shared buffer. All right, so this is extremely basic partition elimination format of your query optimizer in Greenplum. As we move ahead by introducing, say, predicates or joins on tables, it becomes a little bit more complicated. Now, one of the questions that commonly comes out is like, why was this introduced, right? So what benefit does it offer over your Postgres planner? So the very first thing is this kind of elimination occurs directly during runtime. So this plan does not know whether the partition has been eliminated during the planning phase. So when it starts getting executed on your Postgres instance, that's when it realizes that it has hit a partition table. It starts creating the partition scan and your dynamic table scans and starts to do its work directly during execution time. So it basically eliminates the need to run like a full table scan during the planning stage. In a warehousing environment, like if you have a lot of partitions, it kind of saves some amount of time when doing that kind of planning in the initial stages. All right. So when you look at this plan compared to the one that we saw on the planner, it's much more compressed. It's much more readable. It's a simple operator calls for partition selector. This is the first one that gets called in terms of your partition elimination. If there is a predicate on top of it, it will tell you exactly how many partitions were selected during this phase. And only when those partitions are now identified, it moves to the next stage where the DTS kicks in and starts to do sequential scans on those partitions. So it kind of eliminates the need to kind of look at everything, right? So much more compressed, much more readable. One disadvantage I would say is if you want to see exactly how many partitions were selected, the Postgres planner does a much better job. It kind of lists exactly which were read, which were executed, and which was skipped. So this is something that kind of diverges out, like you only see the amount of partitions that were selected in form of a number. It doesn't really like give you the complete names. You might have to do some verbose logging, which might tell you the partition key from which you can identify which partitions were selected. But then like the planner is a little bit better in terms of readability if you want to really see which partitions were selected in that case. All right, so in terms of the workflow, right, now let's look at a little bit of a complex workflow where you have a partition table sales, you have a non-partition table order data, and this is where this kind of elimination helps, right? So the sales.year partition column, it's currently not getting a fixed value as input. It's getting a dynamic value from your order year table, the order year column, which needs to be evaluated first. All right, so this is where it helps. So the moment you encounter the join, which is basically a hash join on the sales and the order data table, the join basically starts to look at your sales table and your order data table. It knows that order data is not a partition table, so it does a simple table scan on it. All right, it knows that there is a predicate on your order data table. All right, so it does, this is a select expression in algebraic form. All right, so it does its filtering on the order data table at the very first level. It then needs to feed that value to your partition selector. All right, so the partition selector comes here in this branch because it needs that value from the order data table to further prune the elimination for your sales table, right? So in this case, this particular scan feeds the year value to your partition selector. So the partition selector now knows that the sales table has only a specific number of values that it needs to look at. So the partition selector now does its thing. It starts to create the shared buffer. It starts to load it. And based on the values that you're passing in the year column, it selects those specific partitions. It creates a key value pair And say, for example, out of 50 partitions, it identifies 5 of them. So it creates that key value pair in the hash table. And the buffer is nicely built with exactly the number of partitions that need to be scanned in the next stage. Okay, so after the partition selector is done, it then moves to the DTS phase, which is a table scan. Now the table scan is not a full table scan. It takes a look at your shared buffer, the hash table that it's created. It then starts to load the partitions that exist in that hash table. So it doesn't need to load all the 50. It only needs to load those 5 that were built in the PS stage. All right, so it saves a lot of time. It saves a lot of scans on tables. So in the DTS, it will load all those partitions, read them, and provide them back to your branch ahead. All right. Any questions so far? So the life cycle of the hash exists till the time the sequence exists. So once the DTS completes, sends it back to the sequence. It sends the data back. Once it's done, the hash table is done. No, so the hash table will be unique to each scan. So you cannot use it for other. So even if there is another sales reference in this query, it's a completely different reference, right? It will then create a separate branch with a partition scan and a DTS and its own shared buffer. So it's all independent.
How is this different from the default partition store?
So Postgres does something similar, like it does take into consideration the key values that it needs to sort based on the partition pruning, but that happens in the initial planning stage. It does not do it during runtime. So Postgres with stats, in the initial stage, right, like the Postgres will load what partitions are getting called in terms. Yes, so in the execution phase, based on the predicate that you provided and the join order, it would still do the pruning during the execution, but the plan also has that information before executing it, right? Based on your predicate. Correct. So the difference here is that the optimizer does not do it. Like it does not consider it during the planning phase. It does everything during execution. Postgres does it during planning as well as execution. Does that make sense? So in terms of so overall readability, I would say like the plan with the optimizer is much more compressed. It avoids certain OOM conditions if the plan is extremely big. The optimizer had to implement it because we saw many conditions where if you had 100 plus partitions, the plan would just scale out, become very big. During dispatches, it would lead to out-of-memory conditions, and it would fail. So we had to come up with an idea where we had to make the plan more compressed, very readable and scalable. But then there are some disadvantages. You don't really know what partitions are getting eliminated in this plan. It just numbers them. But outside of that, like the difference is that this is runtime. Starting from 9, 10 onwards. Greenplum currently, the 7 version uses 12. Okay. We then look at a slightly more complicated plan based on our hash join. And now in this case, we also have a predicate on the sales table. The sales table now needs to eliminate 2 partition scans. So in this case, the year partition scan that's been fed by order data. And the second one is your sequence. which gets initiated because of the 2009 value, right? So in this case, it now needs to do a completely different lookup. So there is another partition scan initiated here on this value. So the DTS on sales is now being fed by 2 partition scans, right? So the partition scan here provides a certain list of partitions. The partition scan here also provides a certain list of partitions. So the hash table now has a combination of both of these scans and the one that has an overlap, right? So scans that catch partitions from here and a union which gives both the partitions is now fed to your DTS, right? So the DTS now takes a look at a more convoluted list of partitions based on these 2 conditions and feeds them to the hash join, right? And then the hash join takes care of it ahead. Any questions on this? No? All right, so as I said, like there are some advantages here, like you get compact plans, more readable. You will be able to kind of distinguish the number of partitions that are getting eliminated more quickly. It's the certain limitation is that it just prints the number that's getting eliminated instead of the complete list of names. Planner does an append and a scan. Orca uses like all of these 3 operators. It enhances readability on like complex plans. For example, if you have partitions that are joined multiple times or many tables which are partitions which are joined together, it's more readable. Less memory usage because of the plan size. You don't need to tune max plan size in this case. Otherwise, there might be a situation where you might run out of memory. Optimizer uses stats from your root partition, your root table. Planner uses it across the partitions, right? And in some cases, Orca is much better. Like it always finds a way to facilitate the dynamic elimination of these partitions as it does it during runtime. Planner might not be able to do it in the very initial stage when it's planning the plan. It might do it later on in the execution, but Orca kind of does everything in the executor. So might be possible that Orca kind of does it more quickly than the planner. All right, I'll give you one example of a Postgres plan. So currently we are joining on 2 tables which are partitioned. So if you look at the plan, it's got 25 partitions each. So the plan basically spans 2 slides. So if you go to the next one, it does a full listing of these partitions. The approximate execution time is around 46 milliseconds based on the scans. And then if you compare it with the optimizer plan, and this is what it provides, much more compressed. And because it's done during runtime, I'm assuming it's taking around 21 milliseconds, which is less than half the execution. All right, so you can clearly see the differentiation between the 2. Doesn't mean that planner, the Postgres planner is bad. It just means that like in terms of readability and like if you have tools to read explain plans, like it's much more easier to understand it.
And the use case, right, of the green use case is for
larger tables, right? Too much data partitioned heavily across your BU units, right? So it's much easier to read these plans on a Greenplum environment, right? All right. Any questions? Yes. So yeah, VmWare is hiring folks with Postgres knowledge, especially. Like we want people to work on Greenplum. Greenplum is used heavily across financial institutions, manufacturing companies, These are extremely large-scale data warehousing systems holding petabytes of data. We are leveraging Postgres as our go-to tool to kind of make sure Greenplum gets better. Greenplum 7 is about to come out like 6 months on. So this is a right time to join the team if you want to kind of take a look at it. Please reach out to Divya. She's our engineering director. Yeah. Correct. Machine learning is kind of like a topic that kind of scales out, but we're planning to build on top of it. We are also exploring cloud deployments for Greenplum, Azure specifically, and so it's a little bit separate. Yeah.
So Greenplum uses Apache Madlib, which is a machine learning tool which has several capabilities. So that's also open source. So that works with Postgres too, by the way. So we develop both for Postgres as well as Greenplum. Yeah.
Any other questions? If not, yeah. Are we on time? We have another 10 minutes. All right. Okay. Yeah. We can go switch to the next. Greenplum and how it is kind of catching up with some of the Postgres specific improvements, especially on the statistics side. Greenplum currently at this time does not have a widespread support for correlated or extended statistics. To give a very high level overview, extended stats basically takes into consideration relationships between columns. Currently, like if you see, like statistics are only based off single columns, right? Like extended stats takes into consideration the relationship maybe between column A and B and stores that kind of relationship in your catalog. So if you have a query that is using both the columns as a predicate, right? So it's much more wiser to look at these correlated stats to generate your plans rather than having to base it off single column stats, right? So Postgres currently has functionality to store these extended stats in a table, the catalog table. The optimizer wants to take that advantage because it definitely yields to much faster execution times because these kind of relationships help in evaluating predicates more faster, right? So I wanted to, okay, I can, in the interest of time, just go over it really quick. So Postgres stores statistics, extended statistics in two catalog tables, PGStats ext and PGStats ext data. It has a way to evaluate the relationship between two columns. So for example, you have a zip column and a city column. You know that a zip only belongs to a single city, right? So the factor that determines the relationship between the two is 1, right? So it stores that in your catalog as a factor of 1. So next time when you have a query that evaluates zip and city together, it knows that like if you are looking at a zip value, it will only correspond to one city. So it does not need to go and look at stats for your city column, right? So it knows there is a single row fetch when you are evaluating your zip column, right? So that kind of functionality is helpful when evaluating predicates. Postgres does it currently. Greenplum currently does not have a way to do it. We have features coming up in Greenplum that will evaluate these dependencies between the two columns. And dependencies are of various types, like you can have an n distinct variable, you can have multi-column variates, you can have dependencies like the way I just mentioned between your zip and city. Postgres does it currently. You have a way to like store it in catalog and then evaluate based on your plan preferences. We cannot do it in Greenplum currently, but then there are features coming up in Greenplum that handles this kind of dependency together. All right. There are some Postgres threads. So if Hari, if you switch to the third tab. So in here we've started discussions on like how to include or dump extended stats out, just so that you can have them imported for certain utilities or functions like maybe PG upgrade, PG restore, for example. There is some discussion ongoing in the Postgres forums that want to highlight that. Postgres currently does not support dumping these extended stats out. I don't think it does that even for normal statistics. So, for folks who are interested, you want to contribute like to these discussions, please do so. Like, all right. Any questions? If not, yeah. Thank you very much.